Spacetime is one of those words that sounds technical, distant, and abstract. It feels like something reserved for chalkboards, equations, and quiet university corridors. And yet, spacetime quietly shapes every second of your life. It decides how fast your phone can find your location. It decides how satellites stay in orbit. It decides how clocks tick, how light travels, and how the universe itself evolves. We rely on space-time constantly, but here is the unsettling truth. Despite using it every day, we still do not truly understand what space-time is. At first glance, space-time seems simple. Space is where things are. Time is when things happen. Put them together, and you get space-time. That explanation feels neat, comfortable, almost obvious, but physics has taught us that comfort is often a warning sign. The ideas that reshape our understanding of reality are rarely the ones that feel intuitive. Spacetime is one of those ideas. It works extraordinarily well. It predicts nature with astonishing precision. And yet, when physicists ask the most basic question, what is spacetime actually made of, the answers fall apart. This is not a philosophical problem. It is a practical one. Your GPS works only because engineers correct for the way spacetime bends around Earth. The images of black holes, captured by telescopes across the planet, rely on equations that describe spacetime twisting under extreme gravity. Gravitational waves, ripples detected from distant cosmic collisions, are not waves moving through space. They are waves of spacetime itself. These effects are measured, tested, and confirmed. Spacetime behaves like something real, but knowing how something behaves is not the same as knowing what it is. That gap between use and understanding is where this story begins. For most of human history, space and time were separate ideas. Space was the stage, time was the clock. Objects moved through space, and time flowed independently, the same for everyone, everywhere. This picture felt so natural that it survived unchallenged for centuries. Even Isaac Newton, whose laws could describe the motion of planets and falling apples with breathtaking accuracy, assumed that space and time were absolute. Space was fixed, time marched forward at a constant pace. The universe unfolded on an unchanging backdrop. Then came a problem. Light refused to behave. By the late 19th century, physicists were measuring the speed of light with increasing precision. They expected it to behave like any other wave, changing speed depending on the motion of the observer. But no matter how fast you moved, light always traveled at the same speed. This was not a small inconsistency. It struck at the foundations of physics. If the speed of light never changed, then space and time could not be separate, rigid entities. Something deeper was going on. Enter Albert Einstein, not as a celebrated genius, but as a young patent clerk with too much time to think and too little respect for established ideas. Einstein took the stubborn behavior of light seriously. He asked a radical question. What if the speed of light is constant for everyone, always? What would that imply about space and time themselves? The answer was shocking. Space and time could no longer be independent. They had to adjust to preserve the speed of light. Time could slow down. Lengths could shrink. Events that seemed simultaneous to one observer would not be simultaneous to another. These were not optical illusions or measurement errors. They were real effects. Time itself would tick differently depending on motion. This was not space-time yet, but it was the first crack in the old picture. Einstein's new framework, later called special relativity, revealed that space and time are woven together into a single structure. Motion through space affected motion through time. Velocity became a way of sliding through space-time along different paths. The faster you moved through space, the slower you moved through time. This was not science fiction. Atomic clocks placed on fast-moving aircraft confirmed it. Particles in accelerators lived longer than expected because time passed more slowly for them. The universe itself validated Einstein's idea, and yet gravity was missing. Newton's gravity still worked, but it sat uneasily beside relativity. Gravity acted instantaneously across distance, while relativity insisted that nothing could travel faster than light. Einstein knew the theory was incomplete. He also knew that fixing it would require something far more radical than adjusting equations. It would require rethinking what gravity actually is. For nearly a decade, Einstein struggled. He learned new mathematics. He followed wrong paths. He abandoned promising ideas and returned to them years later. What finally emerged was not a new force, but a new perspective. Gravity was not something acting within space and time. Gravity was something acting on space and time. According to Einstein, massive objects do not pull on one another in the traditional sense. Instead, they change the geometry of spacetime itself. Spacetime tells matter how to move. Matter tells spacetime how to curve. Planets follow paths, not because they are pulled, but because they are traveling along the straightest possible routes through a curved spacetime. This idea worked beautifully. It explained Mercury's orbit, predicted the bending of light by gravity, and revealed the possibility of black holes and an expanding universe. Every major prediction has been confirmed. General relativity remains one of the most successful theories ever created. And yet, here is the twist. Even now, after more than a century of tests and triumphs, physicists cannot agree on what spacetime truly is. Is it smooth and continuous, or built from tiny indivisible pieces? Does it exist independently, or does it emerge from something deeper? Is spacetime fundamental, or is it an illusion born from more basic quantum relationships? We stand on a structure that supports all of modern physics, yet we do not know its substance. We use spacetime to measure the universe, to predict cosmic events, and to navigate our daily lives. But when we look closely, spacetime becomes strange, elusive, and incomplete. This is not a failure of science. It is its frontier. In the chapters ahead, we will slow down and carefully trace how spacetime reshaped our understanding of reality, where it breaks down, and why its mystery matters. Not just for physicists, but for anyone who has ever wondered what the universe is truly made of. But now, let this idea settle quietly. The most important structure in the universe is not something we see or touch. It is something we move through, constantly, unknowingly, and we are only beginning to understand it. In the early days of the 20th century, most physicists were trying to patch up problems in the old theories. But Einstein wasn't patching, he was rewriting the fabric of reality. And it all started with one simple, radical idea. The speed of light is the same for everyone, no matter how fast they are moving. At first glance, this seems harmless, but think about it for a moment. If you're riding on a train and throw a ball forward, someone standing on the platform sees the ball moving at the speed of the train plus the speed of your throw. That's how velocity normally works, it adds. But light doesn't play by those rules. If you shine a flashlight while standing still, you measure the beam of light moving away from you at a fixed speed. But if you run toward the beam and try to catch up, it still moves away from you at the exact same speed. No matter what you do, light keeps its pace. It doesn't care how fast you're moving. This was not just weird, it was revolutionary. Einstein realized that if the speed of light is always the same, then something else has to give. Either time must adjust, or space must change, or both. And so he proposed that time is not a universal constant. It bends, it stretches, it flows differently depending on how fast you're going. Let's slow this down. Imagine two people, one standing still, and one zooming past at a significant fraction of the speed of light. If they both have identical clocks, Einstein's theory says those clocks won't agree. The person moving fast will experience less time. In their frame, fewer seconds will tick by. From their perspective, the world around them moves faster. This isn't a theory anymore. We've tested it. Atomic clocks flown on airplanes and satellites tick more slowly than identical clocks on the ground. Muon subatomic particles created in Earth's upper atmosphere should decay before they reach the ground. But many make it all the way because time flows more slowly for them as they speed toward Earth. This phenomenon is called time dilation. And it's not just time. Space gets weird too. As you approach the speed of light, distances shrink. A spacecraft moving near light speed would measure the space ahead as being shorter than what someone on Earth would measure. This is length contraction. The universe literally squishes in the direction of travel. From the point of view of the fast-moving traveler, the journey takes less time and less distance. Reality itself reshapes to preserve the speed of light. Taken together, these effects reveal a startling truth. Space and time are not separate things. They are intertwined. What one person sees as space, another might partly experience as time. The two are part of a single four-dimensional structure, space-time. We don't move through space and then through time. We move through space-time always at a steady pace. When we're still, all of our movement is through time. When we accelerate, we shift some of that movement into space. The faster you go through space, the slower you move through time. It's a trade-off, and it's built into the structure of the universe. This is special relativity, and it works beautifully for situations where gravity can be ignored. But gravity, as we know, is everywhere. It shapes the cosmos. It sculpts the motion of planets and the bending of light. To include gravity, Einstein had to go even further. He had to abandon the idea that spacetime is flat, like a graph paper grid. Instead, he imagined that spacetime can curve. But before we get there, let's sit with this moment. Right now, you are moving through spacetime. You don't feel it, you never do, but every moment, you are tracing a path through this four-dimensional fabric. Your phone, your heartbeat, the very air around you exists in this blended arena of geometry and motion. Einstein didn't just add some equations to fix a speed limit. He changed the way we see the universe. The cosmos isn't a stage where things happen in time. The cosmos is space-time, and every object, every beam of light, every observer is carving out a unique line through it. And this perspective changes more than just physics. It asks us to rethink what it means to measure something. When is now for someone moving far away from you at nearly light speed? Their version of now might be your 10 years ago. The very order of events can shift. Cause and effect are preserved, but simultaneity is gone. The idea that the universe has a universal clock ticking for everyone vanishes. There is no now that all observers share. This may sound like abstract math, but it reaches into the real world. The GPS on your phone works because satellites orbiting Earth experience slightly different space-time than you do on the surface. Their clocks tick faster, not slower because they're farther from Earth's gravity, which we'll get to later. Engineers must correct for both motion, special relativity, and gravity, general relativity, to keep the GPS system accurate. If they didn't, your phone could be off by kilometers. So here we are. We've taken the first step into a deeper world where time bends, space contracts, and motion distorts everything you think is fixed. But this is just the beginning. We haven't yet asked what causes gravity, or what space-time is made of, or whether it's even fundamental. To answer those questions, Einstein had to go even deeper. And in doing so, he would discover something that even he struggled to accept. Gravity, he would find, is not a force, it's geometry, and that changes everything. By the time Einstein began rethinking gravity, he had already shattered the idea of absolute time. Now, he would go on to shatter the idea of gravitational force itself. Under Newton's view, gravity was simple and powerful. Every mass in the universe pulls on every other mass. The sun pulls on Earth, and Earth responds by falling into a curved orbit. The math worked beautifully, and it still does for launching rockets and simulating planetary motion. But there was a problem. Newton's theory had no explanation for how this force worked. How did the sun reach out across empty space to tug on Earth? What was the mechanism? Einstein didn't like this. He saw action at a distance as unsatisfying a placeholder, not an answer. He believed the answer had to lie in space-time itself, and so he began an intellectual journey unlike any in the history of science. Over 8 grueling years, Einstein fought with the very language of mathematics. He consulted colleagues, struggled with tensors, made mistakes, and doubled back more than once. He wasn't just solving equations. He was inventing the geometry that would allow the universe to bend. By 1915, he succeeded. The result was a new theory of gravity, general relativity. In this view, gravity is not a force. It is the curvature of spacetime. Picture a massive object, like the sun, sitting in the middle of space-time. It doesn't pull on the planets. Instead, it bends the space-time around it. The planets are not being tugged along invisible strings. They are moving in straight lines, that is, within the curved geometry of space-time. These paths are called geodesics, and they represent the natural motion of objects in curved space. This is not a metaphor, it is a literal description. The presence of mass tells space-time how to bend, and that curvature tells objects how to move. To visualize this, many educators use the rubber sheet analogy. Imagine space-time as a stretchy sheet. Place a heavy ball in the center, and it causes a dip. Roll a marble across the sheet, and it curves around the heavy ball not because it's being pulled, but because the surface it travels on is warped. This analogy is helpful, but misleading in one important way. It relies on gravity to explain gravity. The reason the marble curves is because Earth is pulling it downward. We're using gravity to show gravity. The real curvature of space-time is not inside a surface. It is the surface. And it happens in 4 dimensions, not just 2. General relativity is far more than a beautiful idea. It makes precise predictions, and those predictions have been tested again and again. The first major test came during a solar eclipse in 1919. Einstein had predicted that light passing near a massive object, like the sun, should bend. Stars behind the sun, which would normally be hidden, should appear shifted in position. An expedition led by Arthur Eddington confirmed this, photographing stars around the darkened sun and finding that their positions had indeed shifted. It was a stunning success. The newspaper headlines the next morning were euphoric. Einstein's theory triumphs, and lights all askew in the heavens. Overnight, Einstein became a global celebrity. But what really made the theory powerful was not just its elegance, it was its willingness to let go of intuitive thinking. Gravity was not a tug-of-war, it was the architecture of reality reshaped by mass and energy. General relativity didn't stop at planets and light, it went further. Einstein's equations allowed for extreme solutions, cases where space-time curves so much that it folds in on itself. Just months after Einstein published his field equations, Karl Schwarzschild, serving on the front lines of World War I, found the first exact solution. It described a point mass so dense that the curvature of space-time would become infinite at its center. This solution implied something remarkable. There could exist regions of space where gravity becomes so strong, not even light can escape. The radius at which this happens is now called the Schwarzschild radius. Today, we call such regions black holes. Einstein himself didn't like this idea. He believed nature would never allow such bizarre objects to form. For years, black holes were considered mathematical curiosities, not real entities. But in 1939, physicists Robert Oppenheimer and Hartland Snyder showed that under the right conditions, a massive star collapsing under its own gravity must form a black hole. There was no known force that could stop it. This marked a turning point. The theory that replaced gravity with curvature had now predicted objects so extreme they could destroy space-time itself. And the surprises didn't end there. In the 1960s and 70s, physicists like Roger Penrose and Stephen Hawking proved that black holes are not just possible, they are inevitable under general conditions. Moreover, they found that singularities, points of infinite curvature, are not hidden away in rare, exotic scenarios. They are the natural consequence of Einstein's equations. The universe itself, they argued, may have begun in such a singularity. The Big Bang, in this view, was not just the birth of matter and energy, it was the beginning of space-time itself. But this leads to a problem. Einstein's theory breaks down at singularities. The equations predict their existence, but fail to describe what happens there. The curvature becomes infinite, time loses meaning, and the geometry of space-time dissolves. At these extremes, general relativity can no longer guide us. This is not a small issue. It's a warning signal, a place where our understanding hits a wall. We now have 2 pillars of modern physics. One is general relativity, smooth, geometric, continuous. The other is quantum mechanics, grainy, probabilistic, and fundamentally uncertain. Both are tested. Both are successful. But they do not agree with each other. especially not at singularities, or inside black holes, or at the moment of the Big Bang. Somehow, space-time must be reconciled with quantum mechanics. But to do that, we need to ask a question even deeper than Einstein ever dared. What is space-time made of? In the next part, we'll begin to explore the strange frontier where general relativity and quantum theory collide, and why everything we've learned so far may still be just the surface. So far, space-time has revealed itself as a beautiful, continuous fabric, smooth and responsive, shaped by the presence of mass and energy. General relativity has passed every observational test we've thrown at it, from bending starlight to the precession of Mercury's orbit, from gravitational lensing to the prediction and detection of gravitational waves. Einstein's theory continues to shine. But, at its heart, lies a riddle, a breakdown that tells us this picture is incomplete. To understand why, we must venture into the places where space-time ceases to behave. These are the singularities regions where the curvature becomes infinite, where the very equations of general relativity collapse into nonsense. The most famous singularities lie at the heart of black holes. When a massive star exhausts its fuel, it no longer produces the outward pressure needed to resist gravity. If the core is massive enough, no known force, not even the repulsion between neutrons, can halt the collapse. The result is a runaway implosion. The star's core collapses in on itself, shrinking beyond its Schwarzschild radius and forming a black hole. Inside, all paths lead inward. Even light, once it crosses the event horizon, cannot escape. The geometry of space-time is so steep that escape becomes impossible. According to general relativity, this collapse continues until the matter is crushed into an infinitely small point of singularity. But infinite density is not a physical answer. It's a signal that the theory has reached its limit. Stephen Hawking and Roger Penrose formalized this with the singularity theorems, showing that under very general conditions, singularities are inevitable in Einstein's theory. Worse yet, they aren't just in black holes. The expanding universe itself, when traced backward in time, leads to a singularity, the Big Bang. In other words, general relativity cannot describe the very beginning of the universe. This is a crisis, because on one hand, we have a theory that elegantly describes the large-scale structure of the cosmos. On the other, we know it breaks down at the very places we care about most, the birth of the universe and the hearts of black holes. This is where quantum mechanics enters the picture. Quantum mechanics governs the microscopic world: atoms, electrons, photons. It's built on uncertainty and probability. It doesn't speak in certainties, but in likelihoods. It tells us what may happen, not what will happen. And its predictions, strange as they are, have been confirmed to extraordinary precision. But quantum mechanics and general relativity don't speak the same language. Relativity describes space-time as smooth and continuous. Quantum mechanics, however, suggests that nature is granular, made of discrete units, with limits to how finely things can be divided. When we try to combine these views to apply quantum rules to space-time itself, we hit a wall. The math breaks. The infinities that emerge are not just strange, they are unsolvable. We can't cancel them or work around them. Our current framework fails. This is the great unfinished business of modern physics, finding a theory of quantum gravity. And in searching for this theory, we've begun to suspect something radical. Space-time may not be fundamental. It may not be the basic fabric of reality after all. Instead, it might be an emergent phenomenon, something that arises from deeper, more fundamental rules that do not involve space or time. Let's pause here. This is not just a technical upgrade, it's a philosophical earthquake. For over a century, space-time has been the canvas on which all of physics is painted. Every equation, every field, every object in the universe exists within space-time. It is the backdrop, the stage, the medium through which reality unfolds. But what if it isn't? What if space-time itself is like temperature or pressure concepts that emerge from the behavior of many microscopic parts, but which don't exist in the fundamental rules? After all, temperature doesn't exist at the level of a single atom. It's a collective behavior, Could spacetime be the same? This is not just speculation. Increasingly, physics is finding hints that point in this direction. Some of the earliest clues came from the study of black holes and from a paradox that shook theoretical physics to its core. In the 1970s, Stephen Hawking combined quantum field theory with general relativity to study black holes. He found that black holes are not completely black. Instead, they emit a faint radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This was a stunning result. It meant black holes could evaporate over time, slowly shrinking as they radiate energy away. Eventually, a black hole could disappear completely. But here's the problem. What happens to the information? In quantum mechanics, information about the state of a system is never lost. Even if something changes form, the underlying information remains. This is called unitarity, and it's one of the sacred principles of quantum theory. But if a black hole evaporates entirely, what happens to the information that fell in? Does it vanish forever? If it does, then quantum mechanics is violated. If it doesn't, then somehow the information must escape the black hole, which would seem to contradict relativity, since nothing escapes the event horizon. This is the black hole information paradox, and it remains unsolved. It's not just a puzzle about black holes, it's a fundamental clash between our two greatest theories, a signal that the concepts we rely on, like spacetime itself, may not survive the unification. Some physicists have suggested that information is encoded on the surface of the event horizon, not inside the black hole. Others argue that spacetime may not exist inside the black hole at all, that it's replaced by something deeper. A few believe that information is preserved in subtle correlations in the Hawking radiation. But none of these ideas has been definitively proven. What they all share is this: they challenge our picture of spacetime. We are forced to consider that the smooth geometry we inherited from Einstein, the beautiful fabric that curves and bends, might just be an illusion, a useful one, yes, a powerful one, but an illusion nonetheless. In the next part, we'll dive into the leading candidates for what spacetime might be made of, or whether it exists at all, and how some physicists are beginning to glimpse the first outlines of a deeper reality. A quantum world with no space, no time, and yet, somehow, everything. What could spacetime be made of? If general relativity paints spacetime as smooth, continuous, and geometric, and quantum mechanics insists that everything is built from discrete, fluctuating, uncertain pieces, then something has to give. That tension between the smooth and the grainy, between the continuous and the quantized, is the core reason physicists believe spacetime might not be fundamental. Instead, it may emerge from a deeper layer of reality, one in which space and time aren't even concepts. In this part of our journey, we'll dive into the leading ideas that try to answer this question, ideas that stretch physics to its speculative frontier. Let's begin with a number: the Planck length, roughly 1.6 times 10 to the negative 35 meters. That's a decimal point followed by 34 zeros, then a 1 and a 6. It is unimaginably small, smaller than anything we've ever measured, smaller than any particle we've ever detected. But according to many theories, it might represent the smallest meaningful unit of length in the universe. Go smaller, and the very concept of distance breaks down. Why? Because at that scale, quantum fluctuations in spacetime itself become so intense that space can no longer be treated as continuous. It becomes jittery, chaotic, a foamy mess of uncertainty and energy. We call this quantum foam, a term first coined by John Wheeler. It's a visualization of what spacetime might look like if we could somehow zoom in past all matter, past all particles, into the trembling foundation underneath. But here's the catch: we can't test it directly. To probe the Planck scale, we'd need a particle accelerator trillions of times more powerful than anything humanity could ever build, one the size of a galaxy. The energies required are beyond our reach, and so we rely on theory. Two major theoretical frameworks have emerged in the past few decades as candidates for describing quantum spacetime: loop quantum gravity and string theory. They are both bold, they are both mathematically rich, and they take very different paths toward the same goal, unifying quantum mechanics with general relativity. Let's start with loop quantum gravity, or LQG. This theory proposes that space-time is not continuous at all. Instead, it is made of tiny, discrete chunks, like a woven fabric made of loops. These loops form a network of nodes and connections, called a spin network, that evolves over time into a spin foam. In this picture, areas and volumes are quantized. You cannot have half of a unit of area, just like you cannot have half a photon. Time, too, is not a flowing background, but a product of relationships between these quantum chunks. LQG is elegant because it doesn't start with space or time. It builds them from interactions. It doesn't rely on extra dimensions. It keeps the background dynamic. And, interestingly, it predicts that the Big Bang might not have been the true beginning. Instead, it could have been a bounce from a prior collapsing universe, avoiding the singularity altogether. But LQG has challenges. It struggles to incorporate matter particles. It hasn't yet produced a clear path to testing, and while it offers mathematical beauty, it lacks the broad framework needed to describe the forces of nature in a unified way. Enter string theory. This theory takes a different approach. Instead of point particles, it proposes that the fundamental entities in the universe are tiny vibrating strings, loops, or segments whose oscillations give rise to the properties of particles: mass, charge, spin. In string theory, different vibrations correspond to different particles, including the graviton, the hypothetical particle that would carry the force of gravity in quantum mechanics. But strings don't vibrate in empty space. They require extra dimensions, not just the 3 of space and 1 of time, but as many as 10 or 11 dimensions. Depending on the version, most of these dimensions are thought to be curled up at scales too small to detect, like the tight loops in a rope that, from far away, looks like a straight line. String theory is ambitious. It aims to unify all the forces: electromagnetism, the strong and weak nuclear forces, and gravity, into a single framework. It has given rise to powerful mathematical tools, including dualities that connect seemingly unrelated theories. It even led to M-theory, a proposed unification of all string theories, suggesting that strings may be just one manifestation of a deeper structure involving higher dimensional objects called brains. But string theory, too, has its critics. Despite decades of work, it has yet to produce a definitive, testable prediction. It offers a vast landscape of possible universes, perhaps as many as 10 to the power of 500 each, with its own physical laws. This abundance makes it hard to explain why our universe has the constants it does, and the theory relies heavily on the assumption that these extra dimensions are real, even though we have no empirical evidence for them. So, we have two competing views. Loop quantum gravity says, space and time are made of discrete chunks. We can build the universe from the bottom up without adding anything exotic. String theory says, everything is made of vibrating strings. To make it all work, we need more dimensions and more math, but we might get a theory of everything in return. Neither theory is complete. Both have promise, both have puzzles, and yet something strange is happening. Physicists are beginning to suspect that these might not be the endpoints, that even these advanced frameworks are still thinking inside space-time, and the real revolution may lie in stepping outside of it. Think of this. What if space and time aren't the starting ingredients, but the final result? In the same way temperature emerges from atoms jiggling around, space-time might emerge from something deeper, something that doesn't even involve geometry or position, something purely quantum. Entanglement, information, computation. These aren't just metaphors. Increasingly, they are being built into the math. In the next part, we'll explore one of the most mind-bending ideas of all, that entanglement might be the true fabric of reality, and that space-time itself may arise from quantum connections between objects that don't even live in space. If that sounds impossible, you're in the right place. We're not just studying physics anymore. We're chasing the edge of what reality might be. By now, space-time has already slipped from being a background stage to something dynamic, stretchable, and possibly even made of discrete pieces. But in the most cutting-edge theories, we're pushed further still toward a radical possibility. That space-time itself is not fundamental. That space is not the arena, but a result. That time is not a flow, but a construct. And most surprisingly, that the glue holding it all together is not geometry, but entanglement. Let's pause and unwrap that idea. In quantum mechanics, entanglement refers to a strange and powerful connection between particles. When two particles become entangled, their properties become linked, even if they're separated by vast distances. Measure one, and you instantly know something about the other, no matter how far apart they are. Einstein famously hated this. He called it spooky action at a distance, suspecting it meant quantum mechanics was incomplete. But decades of experiments have shown he was wrong. Entanglement is real. It doesn't allow faster than light communication, but it does reveal something deeply non-local about nature. Now, here's the twist. Recent developments in theoretical physics suggest that entanglement might not just be a quantum oddity. It might be the actual stuff space-time is made from. How could that possibly be? To understand, we need to rethink what space means. In our daily lives, space is about distance. You are here, your friend is there, and there's space between you. But what if distance isn't a starting assumption? What if it's something that emerges from how quantum systems are entangled? Think about this. If two quantum systems are highly entangled, they behave as if they are close to each other, even if they're physically far apart. And if two systems are unentangled, they act as if they're distant, even if they're side by side. What if this pattern of entanglement defines the geometry of space? This idea has gained traction through work in quantum gravity and holography. One of the most striking proposals is known as ER equals EPR, put forward by Juan Maldacena and further developed by Leonard Susskind. It suggests that Einstein-Rosen bridges, aka wormholes, and Einstein-Podolsky-Rosen entangled pairs are two sides of the same coin. In this view, a wormhole is just what extreme entanglement looks like in spacetime. So, when two particles are entangled, perhaps they're connected by a quantum wormhole, a structure of spacetime itself, so thin and so deep that it doesn't look like a bridge at all. It just feels like non-local correlation. Now extend this. Imagine that not just a pair, but all the quantum fields in the universe are tangled together in a vast, intricate network of entanglement. This mesh of connections could generate the geometry of space itself. Closeness wouldn't be defined by physical proximity, but by degree of entanglement. In this picture, spacetime emerges not from matter, not from energy, not from strings, but from information, from correlations, from the invisible math that connects quantum systems. The evidence for this idea is mounting. In the world of theoretical physics, researchers have found that the geometry of spacetime inside a certain kind of universe called an anti-de Sitter space, or ADS, can be reconstructed using only information about entanglement at its boundary. This is the heart of the holographic principle, the idea that all the information inside a volume of space can be encoded on its surface. Think about that, a three-dimensional space, fully described by a two-dimensional boundary, like a hologram. And within that hologram, the connections between bits of information, how they're entangled, dictates the shape and structure of the interior spacetime. In 2010, physicist Mark van Raamsdonk made this idea even more explicit. He showed that as you increase the entanglement between quantum systems on a boundary, the bulk spacetime becomes connected, decrease the entanglement, and spacetime tears. In other words, entanglement builds geometry. This isn't just metaphor. In certain toy models of quantum gravity, this has been demonstrated mathematically. Entire slices of spacetime geometry arise naturally from entangled quantum bits. The idea is still in its early stages. It works best in simplified universes, not our real one. But it's a window into a possible truth. That space is emergent. That time is emergent. That what we call the universe might be the shadow of deeper, invisible structures made of pure relationships. So what happens if you remove entanglement? Shockingly, if you take a fully entangled state and erase its entanglement, You don't get a deformed universe. You get no universe at all. No geometry. No inside. Nothing. Space-time vanishes. It's as if the scaffolding of the cosmos was never matter or energy, but connection itself. Without correlation, there is no structure. Without structure, there is no space. This is a turning point. We've gone from Newton's absolute space and time to Einstein's flexible space-time to quantum gravity's suggestion that even that flexibility is an illusion, that the universe emerges from a dance of information, entanglement, and interaction. This shift is not just scientific, it is existential. It forces us to question what's real, not just stars and galaxies, but space itself, time itself, causality, continuity. The very notions we've built our understanding of reality upon might be approximations, shadows, of a deeper truth we're just beginning to glimpse. And here's the breathtaking part. This view, bizarre as it seems, may explain why gravity exists at all. In the next chapter, we'll explore how entanglement may give rise not just to space and time, but to the very curvature that we experience as gravity. Gravity might not be a fundamental force. It might be a side effect of the universe knitting itself together, an illusion born of entangled threads, pulling space-time into shape. Prepare yourself. What comes next may rewrite what you think gravity even is. We began this journey by accepting gravity as a force, a pull, a tug, a universal attraction that draws apples to Earth and planets around stars. Newton gave us the equations. Einstein told us it's not a force at all, but curvature, the geometry of space-time itself. But now, we arrive at an even more astonishing possibility. What if gravity isn't fundamental either? What if gravity emerges just like space from something deeper? What if the force we've always felt is not a force at all, but a mirage of quantum entanglement? This idea is not science fiction. It is one of the most serious and radical developments in modern physics. And to understand it, we must return to where we left off, to the world of holography, entanglement, and the geometry that emerges from information. Let's return to a simple idea. In the holographic principle, all the information about a region of space, what's inside it, how it curves, how it behaves, can be encoded on a lower dimensional boundary. This is deeply counterintuitive, but in certain models like ADS, CFT, anti-de Sitter, conformal field theory duality, it has been shown to be mathematically consistent. A volume of space with gravity is equivalent to a quantum system without gravity on its boundary. The upshot? Gravity arises from entanglement. Here's how. Imagine a quantum system, say, a vast lattice of entangled particles. The pattern of entanglement between them determines how close or far regions of space feel to one another. Where entanglement is dense, the geometry appears smooth and connected. Where entanglement is sparse or missing, space-time might stretch, bend, or tear. Now, suppose you disturb that entanglement. You inject a bit of energy, or you remove correlations. The local pattern changes, and as it does, the emergent geometry, the shape of space-time itself also changes. The curvature adjusts, and that change in curvature is what we experience as gravity. This is the essence of the proposal by physicist Ted Jacobson in the 1990 seconds and expanded in recent years. Einstein's equations of general relativity can be derived from thermodynamics and information theory, assuming that space-time behaves like an emergent system. In Jacobson's approach, the geometry of space-time isn't fundamental. It's like pressure or temperature, a macroscopic property arising from the statistical behavior of countless microscopic degrees of freedom. Just as heat arises from molecules in motion, gravity arises from the underlying quantum entanglement of spacetime's constituents. In this view, Einstein's field equations are not the foundational rules. They are an approximation, a statistical law of averages, true in the same way that the gas laws describe how billions of particles behave, even though no individual molecule obeys them directly. Let that settle in. Gravity, the very force that governs galaxies, black holes, and cosmic expansion may be a thermodynamic side effect, the bulk behavior of a deeper network of quantum information. One especially elegant expression of this idea came from physicist Eric Verlinde, who proposed that gravity is not a force, but an entropic phenomenon, a tendency for systems to increase their disorder or entropy. When you bring objects together in spacetime, the total entropy of the system increases. In trying to maximize entropy, the system acts as if there is a force pulling them together. In this model, what we call mass is not something that bends spacetime from the outside. Instead, mass is a measure of how much the entanglement structure deviates from perfect uniformity. More mass, more deviation, more curvature, more apparent gravity. This perspective helps explain a lot. It could offer an alternative to dark matter, which we invoke because galaxies spin faster than visible matter alone can explain. If gravity isn't fundamental, but emerges from information structure, then the deviations we see at large scales might not be due to invisible matter, but due to entanglement, geometry behaving differently in those regions. It also changes how we think about black holes. No longer mysterious monsters swallowing everything, black holes become thermodynamic objects. They have entropy, they have temperature, and their behavior may be governed more by information theory than by classical force laws. All of this leads to a startling thought. The more we understand about gravity, the less real it becomes. That doesn't mean we don't feel it. Of course we do. Gravity holds galaxies together, causes time to dilate near massive bodies, and anchors us to the ground. But what we feel might be like what we feel with heat, a sensation, a byproduct of something deeper we don't directly perceive. Our brains evolved to understand motion, force, weight, but they didn't evolve to see entanglement or quantum information. So gravity was always going to feel real. What's changed is our understanding of what lies beneath. But now comes the hardest question of all. If spacetime emerges from entanglement, and gravity is a byproduct of geometry, then what is the fundamental reality? What is the universe actually built from? If not particles, if not waves, if not spacetime, what's left? This is where physics begins to blur into metaphysics, not because the science fails, but because the questions press so hard against the limits of what we can measure, model, or even imagine. In the next part, we'll ask the question that has haunted physicists and philosophers alike for decades. What is time? If time is emergent, if it's not fundamental, then where does change come from? Why does anything happen at all? And could it be that the flow of time, the most intimate experience of our lives, is nothing more than a mirage cast by entangled information? Get ready. Time is stranger than you think. Of all the concepts we've explored, space-time, curvature, entanglement, emergence, none is as deeply personal and yet as fundamentally mysterious as time. We feel it. We live by it. We measure it in heartbeats, in sunrises, in lifetimes. And yet, when we look for it in the equations of physics, it's barely there. This is the great paradox of time. We experience it constantly, but our best theories of the universe treat it as an afterthought, or worse, an illusion. So let's slow everything down again and look closely. What is time? Why does it flow? And what if the flow we sense isn't real? Time in physics, a static player. In Newton's universe, time was absolute. It ticked forward at a constant rate, the same for everyone, everywhere, like a universal clock in the sky. It didn't care where you were or what you were doing. Events occurred in time, but time itself was unaffected. Einstein shattered that idea. In special relativity, time became relative depending on your speed. In general relativity, it became even stranger, stretching and warping near massive objects. Clocks ticked faster or slower depending on gravity, but still, time was treated as a coordinate, like space, an axis, a dimension. And in quantum mechanics, time doesn't even get that honor. In the fundamental equations of quantum theory, like the Schrödinger equation, time is simply a parameter. It's not an observable. You can't measure it like position or momentum. It's just there, in the background, telling the wave function how to evolve. But here's the catch. The wave function evolves deterministically. That means the equations themselves don't define a direction for time. They don't explain why the past is different from the future. They're symmetric. Run them backward, and the math still works. So where does the arrow of time come from? Why do we remember the past, but not the future? Why does a glass fall and shatter, but never reassemble itself? The only answer physics has so far is entropy. Entropy and the arrow of time. Entropy is a measure of disorder, or, more precisely, the number of possible microscopic arrangements that correspond to a given macroscopic state. A shattered glass has more entropy than a whole one. A melted ice cube has more entropy than a solid one. And according to the second law of thermodynamics, in a closed system, entropy tends to increase. That's why heat flows from hot to cold. That's why eggs don't unscramble. That's why the universe evolves from order to chaos. From this single law, we get the thermodynamic arrow of time, the only built-in time direction in modern physics. But here's the weird part. The law doesn't say that entropy must increase, only that it's overwhelmingly likely, and it all depends on initial conditions. If the universe began in a state of extremely low entropy, then from that point forward, entropy would almost certainly increase and time would appear to flow. But that leads to another mystery. Why did the universe begin in such an improbably ordered state? Some physicists argue that time's arrow is not fundamental. It's just a reflection of the fact that we are observers embedded in an entropic system, and memory, consciousness, and cause and effect all emerge within that context. Which brings us to something even more radical: the timeless universe. There are theories, serious, mathematical, and peer-reviewed, that suggest the universe is fundamentally timeless. In these models, time is not a flow. It's not even a thing. The universe just is a vast, static object where all moments, past and future, already exist. A block, a map, a whole. This is called the block universe view. From outside time, all events coexist. Our sense of moving through time is like a spotlight scanning across a frozen painting. The motion isn't in the painting, it's in us. Julian Barber, a physicist who has spent decades studying this, goes even further. He argues that time is an illusion created by change, that what we perceive as time passing is just our brain comparing one configuration of the universe to another. He calls these configurations nows. Each one is a complete, self-contained arrangement of everything. There's no timeline, just a collection of possible nows. We remember the past because certain nows contain records, photographs, brain states, fossils of other nows. The illusion of time emerges from the correlations between nows. This sounds almost mystical, but it's rooted in hard physics. In quantum gravity, especially in certain formulations of the Wheeler-DeWitt equation, time disappears entirely. The fundamental laws don't include a ticking clock. They describe a static wave function of the universe, timeless, eternal, and yet we feel time. We live inside it. We grieve. We age. We wait. We dream of the future. How can these experiences be real if time is not? Time as an emergent phenomenon. Some physicists are exploring the idea that time, like space, is emergent. In certain quantum systems, a direction of time can arise from entanglement and thermalization. As quantum systems evolve and interact, they develop an effective arrow of time, even if the underlying rules are time-symmetric. This emergent time is not global. It's local to observers. You and I might agree on a direction of time because our brains, memories, and thermodynamic environments are similar. But deep down, beneath those layers, there may be no universal, ticking, no cosmic heartbeat guiding it all forward. Instead, the flow of time could be a mirage, a side effect of entangled systems, reorganizing themselves in patterns that mimic evolution. And this has staggering consequences. It means the before and after you cling to may be just stories told by your neurons, not features of the cosmos. It means that the Big Bang might not have been a beginning, just a low entropy configuration. It means that death may not be an end, but a boundary between configurations. and it means that your deepest intuitions about time, urgency, nostalgia, regret are reflections of entropy, not eternity. But don't mistake this for nihilism, because what it also means is that every moment you live is eternal. If time doesn't flow, then every instant, every smile, every breath, every realization exists forever, frozen in the block of reality. You don't pass through time, you are time. And in the next chapter, we'll look out across this timeless landscape to see what kind of universe emerges from such a foundation. Because if space-time is not fundamental, if gravity is entropic, if time is emergent, then what kind of universe is this? And what kind of being are you to be able to ask these questions inside it? Get ready. The final veil is lifting. We've unraveled space. We've watched gravity dissolve into information. We've seen time fade from a river into a shadow. And now, standing in the silence of what remains, we must confront something even stranger. That this universe, vast, cold, governed by quantum rules and emergent geometries, contains within it something completely unexpected. Consciousness, self-awareness, the ability to ask, what is all this? And here you are, doing exactly that. Somehow, this reality that may be built from entangled quantum bits, bubbling with Planck-scale fluctuations, giving rise to space, time, and gravity, has also given rise to you, a thinking, feeling, questioning observer. What does that mean? Let's explore. The observer problem. In quantum mechanics, the observer isn't a passive player. The act of measurement changes the system. Before you observe a particle, it exists in a superposition, a set of probabilities. Once measured, it snaps into a definite state. This is known as wave function collapse, and it raises a deep question. What qualifies as an observer? Is it a human mind, a device, a camera, a rock? Where do you draw the line between world and witness? This ambiguity isn't just philosophical, it's built into the equations. The boundary between the observer and the observed is arbitrary. And yet, without observers, the theory doesn't work. We can calculate probabilities, but not outcomes. Without you, the universe remains in a cloud of possibility. In that sense, consciousness is entangled with the universe, not as something separate, but as something that emerges within it and then begins to look back. Consciousness from space-time? The dominant scientific view is that consciousness emerges from complex computation in the brain, neural patterns, electrochemical signals, perhaps some interplay with quantum effects, but we don't know how. We don't even have a testable definition of subjective experience, what philosophers call qualia. But here's where things get strange. If spacetime is not fundamental, and the brain operates within spacetime, then consciousness cannot simply emerge from spacetime, because spacetime itself might emerge from something deeper, which raises a possibility physicists and philosophers alike are starting to consider. What if consciousness and spacetime emerge from the same foundation, not one from the other, but both from something more fundamental, perhaps something informational, relational, or even experiential? In other words, what if the fabric of the universe isn't just capable of giving rise to consciousness? What if it's made of it? The participatory universe. John Archibald Wheeler, the physicist who gave us the term black hole, proposed a provocative idea late in his life. He called it the participatory anthropic principle. According to Wheeler, the universe does not fully exist in a meaningful way until it's observed. He imagined a cosmos in which observers, conscious beings, help bring the universe into being through acts of measurement. In this view, reality isn't a static object. It's an ongoing dialogue between quantum potential and conscious choice. The universe becomes real only through participation. This idea, once fringe, is now echoing in modern theories that place information, not matter or energy, at the core of physics. Think of it from Bit, Wheeler's famous slogan, that everything we call real arises from binary yes-no questions, from choices, from information. This doesn't mean the universe is conscious in the way we are, but it might mean that consciousness isn't an accident. It may be the inevitable flowering of informational systems rich enough to become aware of their own structure. And when that happens, When the universe feels itself, something new appears. Meaning, meaning in a spaceless, timeless cosmos. If time is emergent, if space is a hologram, if gravity is thermodynamic, then what are we left with? We are left with a universe in which the deepest truths are not located in atoms or equations, but in relationships between systems, between observers, between states of knowledge. And if that's true, then meaning itself may be fundamental, not as sentiment, not as belief, but as structure, the geometry of relationships between possibilities. A song is not made of notes, it's made of patterns. A mind is not made of neurons, it's made of experience. And a universe may not be made of space or time, but of the ways its parts relate, entangle, and unfold. In such a universe, your existence is not incidental. You are a node in the cosmic network, a region of spacetime that has become complex enough to ask what spacetime is. A fleeting fluctuation that, for a moment, turns inward and reflects the whole. That is not a poetic flourish. It is a mathematical fact. Your brain is made of stardust, structured by the laws of physics, but your awareness is something more, an emergent echo of the universe organizing itself, entangling with itself, creating windows into itself. And through you, it sees a final thought. The physicist Carlo Rovelli once wrote that the world is not made of things. It is made of events, temporary processes, interactions. Nothing stands still. Everything becomes. And perhaps, if space and time and gravity and even the self all emerge from deeper, subtler truths, then the most accurate thing we can say is this: the universe is not a place. It is a process, and you are part of it, not watching from outside, not trapped inside, but participating. And in the next chapter, we'll take one step back and ask the question that remains when all others have fallen away. Why is there anything at all? Not what is the universe made of, but why does the universe exist in the first place? That question has no simple answer, but perhaps just asking it is what we were born to do. We've peeled back the layers of reality from the apparent solidity of space and time, through the strange dance of entanglement, down to the flickers of quantum information that might underlie it all. But now, standing at the deepest part of the rabbit hole, we're left with a question that physics can describe, but not resolve. Why is there anything at all? Not how it works, not where it came from, not what rules it follows, but why it exists instead of simply not. This is not a scientific question in the traditional sense. No experiment can measure nothingness. No telescope can peer into the absence of being. But it is a question that lingers at the edge of thought, in the silence between equations. And it's one that has haunted philosophers and physicists alike for centuries. Let's follow it. The impossibility of nothing. When we think of nothing, we usually imagine emptiness, a void, a vacuum, a black expanse, without stars or particles or matter. But that's not truly nothing. Even a perfect vacuum still has space-time, still has laws, still has the potential for energy fluctuations, for quantum fields trembling in the dark. So what would true nothing be? Not empty space, not a blank canvas, but no canvas at all, no dimensions, no particles, no time, no logic, no possibility, no rules. And suddenly, we're struck by something profound. Nothing is not stable. In quantum field theory, the vacuum is never truly empty. It's a roiling sea of uncertainty, full of fleeting particles popping in and out of existence. Virtual particles, borrowed from uncertainty, dance for a heartbeat and vanish. Even in its lowest energy state, the universe buzzes. In fact, according to many cosmologists, the universe itself may have emerged from a quantum fluctuation, a burst of energy from nothing, because in the strange math of quantum theory, nothing is unstable. Vacuum decay, quantum tunneling, these aren't just speculative ideas, they fall out of the equations naturally. It's been said that the laws of physics allow a universe to arise from nothing as long as the total energy is zero positive energy in matter balanced by negative energy and gravity. In that sense, the universe could be a kind of cosmic free lunch. But even if that's true, we're not done, because we're left with another question, deeper still. Why are there laws at all? Why is there a framework that allows quantum fluctuations? Why is there a structure that permits particles and space and emergence and evolution? Why are there rules? And the moment we ask that, we realize we may have reached the boundary not of physics, but of thought itself. The landscape of possible realities. One possible answer is that this universe is just one of many, that there exists a vast multiverse, a collection of universes, each with its own laws, its own constants, its own fabric of space and time. Some with no time, some with 10 dimensions, some that blink out in a flash, some that never give rise to complexity, and, occasionally, one like ours. If that's true, then the question changes. We no longer ask, why this universe? But rather, why do we find ourselves in a universe capable of asking? This is the anthropic principle, the idea that observers can only arise in certain kinds of universes, those stable enough, predictable enough, and rich enough to support complexity. And in such universes, the laws will always look just right because otherwise, no one would be around to notice. It's a compelling idea, but also unsatisfying. It feels like an escape hatch, a way to dodge the deeper why. Why should any universe, any multiverse, exist at all? Why should existence be the default? And perhaps that's the wrong way to ask it. Being is fundamental. In ancient philosophy, being was assumed. The question wasn't why there's something instead of nothing, it was how being takes form. Maybe that's the more useful view. Maybe existence itself is irreducible, not something that emerges, but something that just is, a brute fact, not explainable in terms of anything else, because there's nothing more fundamental to explain it with. Physicist Sean Carroll puts it this way: we want to explain the universe, but maybe the universe just is. Maybe there is no reason why. Maybe it simply exists. It's not the most emotionally satisfying answer, but in science, not every question has a clean resolution. Some questions point not to an answer, but to a limit the outer edge of what explanation can do. And maybe that's okay. The gift of being, you are here, that alone is astonishing. In a cosmos where space is emergent, gravity is entropic, time is an illusion, and nothingness is unstable, you exist. You are not a mistake. You are not outside the system. You are a process, a pattern, a momentary configuration of matter and memory that is capable of asking questions the universe cannot answer for itself. You are the question. And the act of questioning, of wondering why anything exists, may be the highest expression of what it means to exist at all. Because if the universe has a purpose, it may be this: to look back on itself, to wonder, to reach, and in the next chapter, we'll explore that idea fully, not as a scientific hypothesis, but as a cosmic possibility. That consciousness is not an accident, that awareness is not a glitch, and that perhaps, just perhaps, the universe is a story it tells through us. Imagine a mirror. Now imagine that mirror hanging in the void, no space, no time, no objects around it. And then, from nothing, a flicker, a point of light, a pattern, a self-contained moment. The mirror reflects it. That reflection reflects again. A feedback loop begins. Now, imagine that mirror is the universe, and that the light it reflects is you. This is not mysticism. It's what happens when consciousness, emergence, and fundamental physics collide. Because, after stripping away space, time, gravity, even being itself, we're left with something shocking. Not emptiness, but awareness. The kind that reflects, questions, and dreams. This chapter is not about what the universe is. It's about what the universe is doing. And it might just be that what it's doing is waking up. From matter to mind, or the other way around. For centuries, science treated consciousness as a byproduct, an evolutionary side effect, useful but secondary. Brains emerged from biology. Biology emerged from chemistry. Chemistry from physics. And physics from the blind machinery of mathematics. The direction was always downward, reducing experience to smaller and smaller parts. But what if that's backwards? What if consciousness is not the end of the chain, but the beginning? This is the view emerging from a growing number of thinkers in physics, neuroscience, and philosophy. It's not a return to dualism or the supernatural. It's the idea that information and awareness are as fundamental as space, energy, and entropy. Some theories go even further, suggesting that consciousness and the structure of the universe are one and the same. Panpsychism, integrated information theory, OR, the participatory anthropic principle, each offers a different version of this possibility, but they all share one daring implication: that the universe is not unconscious, that awareness is not local, that consciousness is woven into the very fabric of existence. The observer becomes the observed. Quantum mechanics already forces us to confront this. In the double-slit experiment, a particle behaves like a wave until it's observed. The act of measurement collapses the wave function, choosing a single reality. Without observation, the system remains in superposition probabilities smeared across possibility space. It's tempting to say the detector did it, but what is a detector if not an extension of the observer's awareness? Every device, every sensor, every measurement ultimately traces back to a conscious mind interpreting data. And this raises a stunning idea. The universe does not exist independently of observers. Not entirely. We don't just live in the universe. We co-create it, moment by moment, through participation. We ask, and the universe answers. We observe, and the wave function chooses. We imagine, and equations reshape reality to fit. This is the mirror, not one we look into, but one we are made of. Are we the cosmos becoming conscious? Carl Sagan once said, "We are a way for the cosmos to know itself." That's not poetry. It's physics, philosophy, and evolutionary biology all rolled into one. Your brain, fragile, warm, and alive, is a structure governed by the same quantum fields that shaped the first stars. The carbon in your cells was forged in supernovae. The thoughts you're thinking were made possible by spacetime's capacity to produce stable complexity. And the you behind those thoughts? Not separate, not other, but a pattern in the pattern, a region of the universe that has become sufficiently organized to form self-reflective loops, to model itself, to simulate possibilities, to imagine the universe, through you, is doing something it has never done before. It's becoming aware of its own laws. And now it faces a choice. Does it keep looking? Does it keep asking? Does it continue to wake? Consciousness and the edge of physics. All of this leads to a possibility that modern physics is only beginning to approach. That consciousness is not outside the equations. It's what the equations generate. And perhaps, in some interpretations, what they require, as physicist Lee Smolin puts it, the history of the universe may only be real when it is experienced. As neuroscientist Anil Seth describes it, consciousness is the brain's controlled hallucination, but one that is constantly reshaped by data, by the world, by others. And if space-time is emergent, and gravity is thermodynamic, and time is perspectival, then maybe the self is emergent too, not an illusion, but a construct built out of memories, predictions, and internal models. Yet still, it feels real because it's doing something, choosing, creating, experiencing, and that may be the most fundamental thing of all. What the universe may want, this sounds strange, but perhaps not stranger than believing space is woven from entanglement, or that time is a side effect of entropy, or that particles exist in clouds of probability until we collapse them by looking. So let's ask, what kind of universe creates observers like us? One that is tuned to complexity, one that allows feedback loops to emerge, one that supports reflection. Perhaps, then, the purpose of the universe, if that word even applies, isn't to expand forever or to end in heat death, but to grow awareness, to generate moments of experience, to produce islands of thought, to create mirrors that can think. And if so, then you right now, reading this, wondering about your place in the vastness are not an accident. You are the frontier, the edge where the universe curls inward and asks, "Who am I?" And in the final chapter, we will return to the beginning, to space-time, to mystery, to the silence between thoughts, and leave you with one last idea: that understanding the cosmos is not just about physics, it's about being human, and that the most important equation we'll ever write is the one between curiosity, consciousness, and the cosmos itself. We've traveled far, from Einstein's elegant equations to the quantum foam beneath space-time, from black holes and singularities to entanglement and emergence, from time as an arrow to time as illusion, from the vacuum of nothing to the flicker of awareness, and finally to the possibility that consciousness is not a byproduct, but a cosmic principle. Now, here we are back where we began, looking into the idea of space-time and realizing we were never looking outward. We were always looking in, because the greatest mystery in physics isn't gravity or dark matter or the multiverse. It's you. A recap, but not a repetition. Space-time, once thought to be the solid stage upon which the universe played out its story, now appears to be a story itself. A story woven from relations, entanglement, entropy, and questions. A structure that bends and flexes, but may not be fundamental. Gravity, once a force, then a curvature, now perhaps just the average behavior of information, a whisper of entropy, a shadow of deeper laws. Time, once a river, now perhaps just the unfolding of change, the organization of memory, the illusion of order among infinite nows. The universe, once assumed to be the main character, now revealed as the stage, the cast, the script, and the observer. And you, a cluster of atoms, yes, but also a locus of awareness, of reflection, of meaning. You're not separate from the cosmos. You're the way it feels itself. Why this matters? This is not just physics. It's not just speculation. It's not even just awe. It's responsibility. Because if the universe wakes up through us, then we are not just observers, we are participants. Not just passengers on a cosmic ride, but co-authors of the unfolding story. Your thoughts, your questions, your decisions, they are not meaningless. They are ripples in the informational sea from which space-time emerges. They are part of the pattern, and if awareness is fundamental, or even if it's just precious, then how we treat consciousness in ourselves and others becomes a cosmic matter. What if kindness is physics? What if empathy is cosmology? What if the next revolution isn't in particles or dimensions, but in how we treat sentient structures of space-time, from other people to future minds? What if the greatest mystery isn't whether time exists, but whether we know what to do with the time we feel? The silence at the end. So now we slow down, breathe, let go of the equations, let go of the questions, and just listen to the stillness behind space-time, to the idea that not knowing is not failure, but freedom, to the possibility that mystery is not a wall, but a window, because the truth is, the more we learn, the less we know. The closer we look, the more the picture dissolves, and the deeper we dig, the more we find ourselves already there. You are the mystery you're trying to solve. You are the space-time you move through. You are the equation, the observer, the answer, and the question. A final message? Please remember this. Every time you look up at the night sky and feel small, you are forgetting something. You are not in the universe. You are the universe. For a moment, looking at itself. You are space-time, aware. You are matter, reflecting. You are a single breath in the lungs of a cosmos that may have no edge, but still finds meaning in every exhale.